Okay, in game development, it is important to ensure the difficulty feels right to the user. As Ernest Adams put in his books, a balanced game is fair, neither too easy nor too hard, and makes the player skill the key to success. But game difficulty testing is actually a real tedious process. Big studios can afford to hire teams of testers to play through every level and get estimation of the difficulty. But for small indie developers, that kind of large-scale testing just isn't realistic. So many small or indie studios turn to early access, releasing the game before it's fully polished and rely on the community for feedback. But that approach comes with its own risk. If the early version feels unbalanced, people may leave negative reviews, and those reviews can seriously hurt the game's reputation and future sales. So there's a strong demand in the game developer community for an easy, low cost, and a general method for automated game difficulty testing. Recent advances in large language models make them a promising direction for game testing. Unlike traditional AI approach, LLMs can potentially play games without the need for large-scale training on each specific title. That makes them much closer to a general video game player. For example, using LLM play complex strategic games like StarCraft 2 or turn-based game like Pokemon. These studies shows that LLM can reason, plan, and make decisions in very different game environments, which highlights the potential for being general video game player and testing across a wide range of games. And in this study, we aim to explore the potential of using LMs as a tool for games testing, specifically for evaluating game difficulty. And we frame this through three research questions. Can LM play games in a meaningful way? Can their performance serve as a signal of game difficulty? And does those LM performance correlate with human performance? Note that difficulty in games can mean many different things and is often quite complex. Here, we focus on objective difficulty. Sometimes we can measure from statistic signals like the average win rate of human players. And here's the system structure for our LM game tester. The game environment provides information like game status, available actions, and opponent status. And everything human player would see will be included. This then goes into the I/O component, where it translates the signal to for the LM, and the LM then generates an action, such as play the card on that target, which is sent back to the game, much like a human decision making process. And to make the LM decision meaningful, we add the instruction component, which provide rules, strategies, and prompting techniques like chain of thought. This framework is a general framework and it can be applied to any game with the as long as they have the right input API. We tested it on two popular games of different complexity. So our first game is called Wordle. It's a word guessing game published by the New York Times, and it has millions of players every day. The rule is very simple. You have 6 tries to guess a hidden 5-letter word. After each guess, the game gives you a feedback, and green means the letter is the right spots, yellow means it is in the word but in the wrong spots, and gray means it's not in the word at all. This simplicity makes Wordle a great starting point of our study. The rules are straightforward. It's purely text-based game, so the LM can easily process it without the needing of extra APIs for process the graphics content. And the difficulty signal is also easy to measure. We can just count how many steps in the LMs needs to solve the puzzle. And importantly, there are also large amount of human gameplay data available online, which then we can use them as a ground truth for the difficulty measurement. And this is how we conduct the experiment. We collected 529 distinct Wordle puzzles spanning from March 7 to August 16, 2026. And for each puzzle, we asked the LLM to play it for 10 times. And we recorded the average number of steps is needed to solve the puzzle. That gives us a measure of the LLM's performance. At the same time, we also collect 1.5 million human play records on the same set of puzzles. From this, we calculate the average steps taken by human players, which we use as our ground truth indicator of difficulty. Last, we calculate the Pearson correlation between LMs and human average steps on these puzzles. These steps allows us to understand whether the LM's gameplay performance is close to human performance, and thus whether it can be used as a difficulty indicator. And here are the results. We included a baseline test, the Wordle solver, to do the task. Wordle solver is an optimized bot for solving Wordle problems. So it is very strong in gameplay performance. But we found that LLMs, although they have weaker gameplay performance, meaning they need more steps to solve these puzzles, but they actually show higher correlation with the human gameplay than the Wordle solver. And better LM with better reasoning techniques shows even stronger correlation. So potentially, Wordle shows prominent results for using LMs to evaluate the difficulty of each puzzle. This also suggests that for difficulty testing, stronger AI or algorithms do not necessarily produce better evaluation. Even though LLMs are not the same level as human players, they still show strong correlation with human in terms of the perceived difficulty. We also tested our framework on another more complex video game, which is a popular game called Slay the Spire. And we found similar results to Wordle. For more details, please refer to our paper. To wrap up, our study shows that LM has the real potential as tools for game difficulty evaluation. We see them as best suited for quantitative assessments like difficulty, while more nuanced aspects such as aesthetics or player experience are still better to left for human judgment. And looking ahead, there are several exciting directions for future work, simulating different player styles, detecting unbalanced mechanism, or uncovering unintended gameplay behaviors. Ultimately, we believe this approach has the potential to support low-resource and indie developers, democratize game testing, and even extend the role of LM as general-purpose evaluators in domains beyond gaming. Thank you.